All right, welcome back. In this series, we've been putting together this giant puzzle of electromagnetism, piece by piece. Well, today, we get to place the final, most important piece. And when we do, we're going to unlock the very secret of light itself.
So here's what's on the docket. We're going to see how this last piece of the puzzle reveals how energy actually moves through space. Then we'll get into the math and actually prove that electromagnetic waves have to exist. And to top it all off, we'll see how the whole thing fits together in this beautiful, perfect law of energy conservation. It's going to be good.
Okay, let's dive right in. The key, the thing that unlocks this whole final secret. It's a concept we've been coming back to again and again in this series. I'm talking about the super powerful idea of conjugate relationships.
You know the drill by now, right? We've seen how pairing up these physical quantities, one from our volt system that describes fields and forces, and one from our ampere system that describes sources and flows, somehow always reveals something deeper, something fundamental about energy. But yeah, we've been saving one very, very special pair for last. And here it is, our grand finale pairing. On the left, you've got the electric field, E, from the volt system, and on the right, the magnetic field, H, from the ampere system. Now, this is not just another pair to check off the list. Oh no, this specific combination, this is the key. This is what unlocks the very nature of light itself and how energy actually moves through the universe.
Okay, so we've got our final pair, E and H. So what? What's the big secret it unlocks? Well, to figure that out, let's go back to our big picture map, our EDH framework, and see where this last piece of the puzzle actually fits.
So check this out. When we take the cross product of E and H, something new pops out. We get this quantity we call S sub p, or the Poynting vector. And just look where it lands in our framework. Bam! Right in the center, at the very heart of everything we've been building. And this thing, this vector, it's not just some mathematical curiosity. No way. It has a real, profound physical meaning. So here it is, the big reveal. The Poynting vector literally describes energy on the move. It's a flow of energy through space. The easiest way to think about it is like an arrow. The direction the arrow points, that's where the energy is headed, and how long the arrow is, its magnitude, that tells you how much energy is flowing through a certain area at any given time. We measure it in watts per square meter. It's an energy current.
I love this visual because it makes a really abstract idea feel solid, you know? Energy isn't just sitting still, stored away in some field somewhere. It's actually being transported. It's moving. And you can think of the Poynting vector as the arrow that's pointing the way for this bucket of electromagnetic energy as it's carried through space. It's a fantastic analogy.
And here's where it gets even cooler. This energy doesn't just travel at any old speed. Nope. It moves at the speed of light, c. And get this. That speed is defined only by two fundamental properties of empty space itself, its permittivity and its permeability. That simple little equation right there is just mind-blowing. It's telling us that the speed of light isn't random at all. It's a fundamental constant of our universe, baked right into the fabric of reality.
Okay, so this idea of an energy current feels right, doesn't it? It's intuitive, it's powerful. But this is physics, and intuition, well, it only gets you so far. We need proof. We need to show it with math. So the question is, can we actually prove that this energy wave exists just using the basic rules we've already learned? Let's find out.
And the proof is actually this beautiful piece of mathematical logic. So here's the game plan. We start with our trusty Maxwell's equations, but in a vacuum, so there are no charges or currents to worry about. Then we do a neat little vector calculus trick. It's called taking the curl of a curl on the equations for both E and H. Now, I know that sounds complicated, but trust me, when you work through it and rearrange all the pieces, something amazing just emerges. And this is what we get. This is the result. We end up with an equation that is literally the textbook definition of a wave. What this equation is screaming at us is that how the electric field changes in space is perfectly tied to how it changes in time. That's what a wave is. This is the mathematical knockout punch. It proves beyond any doubt that light has to be an oscillating electromagnetic wave.
All right, so we've done it. We've shown that energy flows and it travels as a wave. So now let's take a step back, zoom out, and see how this all connects to one of the most sacred, unbreakable laws in all of physics, the conservation of energy. The best way to think about this is like cosmic accounting. For any little box you draw in space, the energy books have to balance perfectly. So, Any change in the energy stored inside the box, plus any energy that flows out of the box, plus any energy that gets turned into heat, it all has to sum up to zero. Always. Energy can move around, it can change its form, but it is never, ever created or destroyed.
And the actual equation really just has three main parts. That first term, that's just tracking the change in stored energy. You can think of it as asking, is the balance in our energy bank account going up or down? The second term, the one with our new friend the Poynting vector, well, that tracks all the energy flowing out of our little volume. And the third term, joule heating, that's the energy that gets spent as heat. And the law says these three things must always, always balance out to zero. It's a perfect system. It really shows you how airtight and internally consistent Maxwell's theory really is.
So there you have it. That's the complete theory. We've connected the dots between fields, waves, and the flow of energy. But, theory is one thing. How do we actually take this amazing toolkit and use it to solve real-world problems?
And this is where the rubber meets the road. Knowing the theory is step one, but applying it, that's the real game. For a lot of complex problems, we have to use a technique called spatial integration. And the absolute key, as this slide shows, is picking the right tool for the job, meaning the right coordinate system. If your problem is symmetrical like a sphere, say a point charge, you better believe you're going to use a spherical coordinate system. If you've got a long wire, cylindrical is the way to go. You have to match the coordinate system to the symmetry of the problem. It makes the math 1,000,000 times easier.
And that's it. Our entire framework is now complete. Think about the journey we've been on. We went from the basic rules of vector fields all the way to proving the existence of light waves and understanding how energy flows through the universe. And these aren't just abstract classroom ideas, right? This is the bedrock of our modern world. It explains everything from fundamental forces to the technology in your pocket. So that final question on the screen, it's the perfect place to leave off. The framework is complete. What secrets of the universe will it unlock next? Thanks so much for joining me for this explainer.